Okay, hey everybody. I'm going to do a quick hint through the January 2019 Unit 1 paper. This is Mechanics and Materials, and this first video is a hint through the multiple choice questions. So by a hint through, I'm just going to give you some possible places to start this. So the multiple choice questions, they can be really quite tricky at times, but they can also be relatively straightforward as well. So let's have a look at these ones, and I will just give you some hints. So the first question is a question about a vector quantity. And so a vector quantity, the thing to remember about that is that you're looking for two numbers. A vector needs two numbers because it needs a size and it also needs a direction. So basically, you're looking to eliminate three of these which don't have a particular direction. Okay. Number two, which of the following is equivalent to a kilowatt hour? Okay, so let's think what a kilowatt hour is. Well, kilowatts are units of power. Power equals energy over time. If you want to remember your triangles, you can. Energy over time and power. And so what happens if you then take power and multiply it by time? Power times time, you get energy. And so kilowatt hour is actually the power times the time. And it might not be clear because it looks like it's a hyphen, but what it really means is kilowatts times time, or times hours. Okay, so that's enough of a clue there. It's going to have units of energy, not units of watts of power. Okay. Right. Stokes' law can be used to determine the frictional force on an object moving through a fluid. Right. So to which of the following would Stokes' law best apply? In general, when friction in fluids is considered, you're looking for laminar flow. Laminar flow is when you've got lots of straight line flows and just a small disturbance. So you might have a little bit of a disturbance going around it, okay? So you're looking for, in general, slow-moving conditions and small stuff and smooth things, okay? So that's a bit of a hint there. Right, this type of question, there's a few different ways to do this. So this is a force of 90 newtons that is pushing a box along a ramp of length 10 meters up a platform which is 4 meters above the ground. So what we're really doing is we're saying, okay, what are we trying to do? Well, we're trying to move it up. And we're trying to move it up against gravity. And so the gravitational force is this one, this 200 newtons. And how far are we moving it up? Okay, we're moving it up a total distance of 4 meters. So it's going up 4 meters. And so the kind of force times distance of what we're doing is the gravitational force, because that's what we're working against, times the gravitational distance, which is basically the height. So that's the useful work that we're doing. But what we're actually having to do that is we're actually having to use a different force, 90 newtons, and we're having to push it a greater distance. So what you've got to do is you've got to work out, well, what are we actually doing and what is the useful work that we're getting out of it? So the efficiency is going to be something along the lines of, it's the useful output energy divided by the total input, and then as a percentage. So there'll be times 100 in there, for example. So have a look at which one of these it'll be. Unfortunately, they don't use any units. This is a terrible question. A terrible way. It's terrible. Bad habit. for you to think that it's possible for you to have any kind of meaning associated with unitless numbers, but there you go. Okay, number 5. According to Newton's third law, when two objects interact, they exert forces on each other. Okay, so the main thing to remember with Newton 3 is that it's the same forces, but they act on different bodies, and they're in opposite directions. So, for example, let's say we've got the Earth and we've got me here, and the Earth is going to pull me. Earth pulls me, but I'm also going to pull the Earth. I pull the Earth. And the thing to remember about this is that they are equal and opposite, these forces, but the end result is not the same, because using Newton's second law, F equals ma, you could have the same force, but depending on the mass involved, you'll get different accelerations involved. So, for example, the mass of the Earth is enormous, and that means that the acceleration of the Earth will be small. The mass of the boy, me, in this case, is very small relative to the mass of the Earth, so the acceleration of me will be very big relative to the acceleration of the Earth. So have a look at which of those answers is the best one. A ball is thrown vertically upwards. Which row of the table correctly describes the magnitude of the initial acceleration of the ball? Well, this is a trick. Whenever you're throwing things up, you always have an acceleration due to gravity, which is exactly the same. Now, they are not allowing you to ignore air resistance, and that doesn't matter because they're just saying what's the initial acceleration of the ball. When you throw it up, the acceleration of the ball is just equal to g, and the acceleration of the ball is down 9.81 newtons per kilogram, meters per second squared. And the magnitude of the acceleration of the ball when it's its maximum height is also going to be exactly the same. And they're just asking for the magnitude. So I'm not going to tell you the answer, but the magnitude of the acceleration of the ball will not change. Okay, one end of a 50 centimetre length of wire is attached to a support. A load is attached to the free end of the wire, which extends by 2 millimeters. Okay, so strain, you actually get this. You get the definitions of what that is. So you could go to the end of the paper and look at the definitions that you got for what strain is. And you could remember it. Strain is kind of the change in length divided by the original length, delta x over x, where x is the kind of the natural length or original length. And that's the strain. So how much is the material straining? How much is it changing its length as a percentage or a fraction of the original length? Okay. 8. A ball is dropped, bounces once, and is then caught. Which of the following graphs? I love these questions because these are getting you to really think about this. Okay, you've got to think about this. And what you do is you say, look, what's going on here, what's going on here, and what's going on there. And you've got to match that with what's happening when it moves forward in time. So you've got to say, what would the gravitational potential energy be at the beginning? So a ball is dropped. So the first thing you've got to work out is the gravitational potential energy at the beginning going to be high, low, medium? Well, if it's dropped, right? Okay. It's starting with a high gravitational potential energy. So it absolutely rules out any of those that start here as 0. So it rules those two out. And then the next you've got to say is the gravitational potential energy likely to be changing linearly in a straight line, or is it likely to be changing as a result of a curve? And so I guess, what does it depend on? The gravitational potential energy is going to depend on height. And what's changing? How's the height changing? The height is changing as the distance changes. So you've got to think, over time, what's the relationship between the distance and time? And then you've got to say, okay, so gravitational potential energy is then a proxy. It means it's kind of the same as the height. So you've got to say, okay, so how is the height going to change? Well, you can think about this and then say, okay, height is a distance. So if this was a distance time graph, the gradient of a distance time graph would be what? Would be the velocity. So a straight line will be a constant velocity. And a curvy line will be a changing velocity. So you've got to work out, when a ball is dropped, is it likely to be having a changing velocity or a constant velocity? Okay. The stiffness constant, the Young modulus, are terms used in physics. Which row of the table shows the correct application of these terms? This is an interesting one, actually. I guess this is something you've just got to sort of learn. I mean, it's kind of a look-up, this. There's no point me really explaining this. Stiffness constant and Young modulus. Okay, so I'm going to let you just have a little sort of think about that and just work that out. The one hint that I could give you, I guess, is that a Young modulus is more likely to be something which is more universal. Does that give it away? Kind of does. So what's more universal? A material or a manifestation of that material, as in an object. Okay. Last one, question number 10. Interesting question, this one. And this is a comparison question. So a student uses a balance to measure the mass of a small cube with sides of length x. The student also measured the mass of a larger cube with sides of length 1.5x. You can see the mass has changed from 50 to... No, sorry, the mass has stayed the same. So which of the following is the density of the larger cube in terms of the density of the smaller cube? Okay, so you need to be able to know that density is mass over volume. Technically we use this. And then you've got to say, if the mass is not changing, then you've got the density is basically equal to 1 over the volume. So how is the volume changing? Well, the volume of this, it's a cube, so x times x, or x cubed is the volume. And this one, the volume is 1.5x times 1.5x times 1.5x, or 1.5 cubed times x cubed. So you've got to work out the difference between these two and then kind of do that as a calculation and see which one it comes out at. I mean, you know that it's going to be less, don't you? Because you've got the same mass and it's a bigger volume. So you know the density of the big cube's going to be less. So you can rule out a couple of them. Let's see how you go. Okay, so what I want you to do is just take the advice I've given you and now attack those 10 questions. Boom.